The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Engine, we talk about solar cells. So in the rest of this course, we're now shifting our attention to solar power. We're combining solar to this engine, and particularly solar thermoelectric and solar photovoltaic. And so here, what's important is not, of course, the heat transfer, but really have a system perspective. You'll find out the spectral control is really crucial for the overall system efficiency if you want to achieve anything. So let's review the three modes of heat transfer. This is the first class for some mechanical engineering. This is very simple, but if you come from other fields, this is probably less familiar. But see, we know there are three modes of heat transfer: conduction, combustion, and radiation. And conduction is by the Fourier law, thermal conductivity, heat transfer rate, so that's the power, and that's proportional to the temperature gradient. And convection, we usually characterize with the heat transfer coefficient H, so it's proportional to the temperature difference between the wall and the fluids, which is away from the surface. And there are electric convection and forced convection. And then thermal radiation, we typically talk about the Stephan-Boltzmann law for Blackbody radiation, and then we calculate the heat transfer, radiation heat transfer between surfaces in terms of view factor and emissivity, which we'll go more into more detail since we're talking more now on the radiation part. So the thermal radiation, Planck's law is usually considered the maximum, and we define the intensity as the power leaving the surface in certain direction. So that's the intensity. It's different from power. So this is the power in this direction that we'll characterize by solid angle. As a power in this direction per unit solid angle, per unit area normal to the direction of propagation per unit wavelength. So that's the intensity. So this is what we mean by intensity. It's propagating in this direction. And when we think about the area, this is the area, not this area, but the area projected into the direction of propagation. So EA perpendicular has a cosine theta to that projection. And solid angle is the measure of the angle in space. So if you think about 2D, we use polar angle, right? And polar angle is the arc length divided by radius. Well, solid angle is the area perpendicular to the direction of propagation, EAP here, divided by r squared. So if you take a sphere in space, that's 4 pi r squared, your solid angle is 4 pi. In 2D, polar angle, the maximum is 2 pi, right? So the solid angle is the space angle, and if we do into a spherical coordinate, it's a theta, and then azimut the direction to the phi, then you can show that this is a sine theta, d theta, d phi. So solid angle really included both theta and phi. So that's the definition in terms of intensity. And when we want to calculate, so intensity is the user starting point. In fact, it will be really interesting. You go back and read Planck's law. He had very interesting discussions, very careful, interesting discussions about Blackbody radiation side intensity. The total immediate power of a surface, normalized by surface area, that's what they call the emissive power. So now if you look at we normalize the emissive power, so power equals intensity times the area EA is perpendicular to the intensity direction, so I have cosine theta. and d omega integration. So this is still per unit wavelength. So that's the the emissive power. And for blackbody radiation, the intensity is isotropic. It's the same in all directions. So it's independent of direction. You can take this out, blackbody, and then you have cosine theta, and d omega is sine theta, d theta, d phi. So you go to do the integration, and if we think about the integration, theta is from 0 to 2 pi, right? That's 90 degrees. And phi is as neutral polar, coordinate, the spherical coordinate, that's 2 pi. So if you do the integration, you find out the intensity for blackbody radiation or isotropic radiation, the intensity and emissive power is pi relationship. So that's the emissive power, and Planck's law of blackbody radiation could be either written in the intensity form or in the emissive power form. Apologize that I missed the C square in my previous first lecture. If you go back to the notes, you can add that. So that's the intensity and emissive power. And so this is what we talked, pretty much what we talked before. And if you plot the blackbody radiation curve as a function of wavelength, usually is use a unit of unit micrometer, and you find out the peak or shift as you go to a higher temperature, the peak shifts to a shorter wavelength. So this is with displacement north-6 where this peak happens. Is the maximum radiation, the wavelength where this maximum happens times temperature is about 3,000. So that's the rough number you can remember. And hence, the solar temperature, set temperature effectively is about 6,000. So that's why our IS is 2.5. That's 200 much. The evolution works really well here. And we have not, adapted, so it's interesting that the human adapted the sensitivity to the sun, right? Not at night. Night you're probably sleeping. So if you think about the emission everybody has is 10 micron, right? Because the 300 degree Kelvin has a peak around 10 micron. We sleep, so through night. If you do integrate all the energy in this under all wavelengths, you get a Stefan-Boltzmann constant, 5.67 10 to the minus 8. So this is pretty much what we review, and now I want to plot this into a more convenient form, blackbody radiation, because it's a function of two parameters, wavelength and temperature. But if I normalize this emissive power by temperature phase power, I change it to a small e later, so we're about to change. So if I normalize temperature phase power, you find out this temperature phase power combined with lambda here is combined with lambda t. So now I think about lambda t as one parameter. So this curve now, the blackbody emissive power normalized temperature phase power is really a function just lambda t. So I can have a universal curve rather than each temperature I have a different blackbody curve. And in fact, if you take your maximum, now lambda t, you can say, if you think this lambda t as x, you find out where maximum is, that's Wind's displacement law. When you got this by experiment, and in fact, you see that Wind has an overprice too. And but this is from Planck's theory, you can derive the thing. Okay, so now using this function, we can also calculate the fraction of energy. This is very convenient, particularly in the old days. Even now, for me, it's every time I want to see how much energy in certain wavelengths from the sun, I take this function. and look at table much faster. So this is the fraction of energy between 0 to lambda. That's the integrate between 0 to lambda. And of course, using this function, we can say that eventually we could write this into lambda t fixed power of this is a force, so there should be another t here, and then say lambda t t moved in, because here is the fifth power, here is normalized to fifth power, here I'm normalized only to fourth power, because this is the total. That's the second Bohr-Zumthor. So after I write this, you can say I can do this integration. This function is a function, it's an integral, is a function of lambda t only. Here is lambda t, lambda t, lambda t. So it's lambda t only. Again, so by doing this, I have a universal function that contains, this is the fraction of energy with the wavelengths between 0 and lambda for any temperature t. Right? So if you give me a temperature, I look at the wavelengths, I do that multiplication, I go to check the table, and usually quickly you find out. So that's this is the integrand, that's the small f, that's here, and as a function of lambda t is written in micron Kelvin, and here is the integral. So that's the fraction of energy between 0 and lambda t. Okay? So you can quickly do an exercise. Again, let me take a solar energy, the sun at 6,000 Kelvin, right? A silicon band gap is about 1.1 micron. So 6,000 times 1.1, 66, right? 6,600. So 6,600, if you look at this curve here, this is log scale, so it's harder to read. So roughly 75%. So the other 25% of the solar energy below the band gap wavelength longer is not used at all. So that's the case of when you use a photovoltaic, there's a band gap, and the photons below the band gap does not excite electron pairs, so that part is completely gone, right? And in fact, you can also think for that part, it's better even just filter it out if you can do it cheaply. Why? Because if you your solar cell absorbs it, you will heat up the solar cell, and usually solar cell heats up, the efficiency drop. Okay, so that's the Blackbody. Now let's look at the sun itself, and then of course that on Earth. So the distance, diameter of the sun is 1.4 to the lines, about 1 billion meter. Remember, diameter of the Earth, right? That's 12 million or 13 million meters, and the distance is close to what is it? 10 to the 11, 10 to 12. Is there a label for 10 to 12 for distance? Terameter. Terameter. So 1.5 10 to the 11th power. So that's the distance. And you look at the solar. Of course, the orbital changes. The distance between the sun and the Earth slightly change, right? But you see that this might be high school knowledge for you, but some of you may not aware of this. Actually, in June and July, the solar flux is lowest, right? This from the distance, July you see here, and is the farthest away from the sun, right? Not the farthest. This is the farthest. So the we have the lowest flux, but we have the summer, right? And the reason is not due to the distance, is because the Earth is wobbling a little bit, right? When you surround the sun, you look at the Earth's axis is not perpendicular to the plane of rotation, and it has a 24 degree of 22 or 24. So this is the direction you can see. About 23.5 degree from the normal direction. So this is the normal direction. And because of that, on each side here, the south hemisphere is in the sun, and here the north hemisphere is in the sun. Okay, so that's the tilting, and this actually creates a problem, particularly when you want to track the sun. Right? Say some people do when you use concentration, you have to track you want to maximize your intercepting area, and so that's the tracking. You have to calculate the rotation of the angle of the orb. So here is the blackbody radiation coming from the sun, reaching the Earth's surface. It's the outside atmosphere, and it's close to 58. Different people have cited different numbers. Later on, I'll show you if I use the 5777 Kelvin, I get a overall constant very close to what I agreed solar constant. So this is the it's very close to blackbody overall. And of course, when the sun comes through the atmosphere, you have a lot of things happening. The solar radiation coming in, it will be reflected by the atmosphere. The clouds can scatter light to all directions. Some will go back. And the atmosphere itself will absorb the solar radiation. Depends on what molecular species. Those are the vibrational modes of the molecules. Typically, it's of the few micron range. So it depends on what kind of molecule. You will have different absorption bands. So if the molecules are heavily absorbing, we'll show later on what are those molecules. Then say those photons cannot reach the surface. It's heat up the molecules directly. But there are with transparency windows. Again, this is pretty lucky for us, right? If everything is just absorbed by all the molecules, we don't have direct sunlight, and we'll feel dark. So, and of course, there are also once you reach the surface, you will have the reflection from the surface of the Earth. So when you put a solar panel there, you have direct sunlight. You also have scattered light from the atmosphere and from the ground. Okay, so this is to characterize solar cell, right? People have to compare orange to orange. So they are scattered in terms of what you should compare. And this solar spectrum linked by the air mass, right? Which is the ratio of the path length of the air, the wind travel through, to the shortest possible path length. So if the outside atmosphere is AM0, and then AM1, air mass 1, occurs when the sun is directly overhead. Okay? And AM1.5 occurs when the sun rays travel through roughly 50%, travel through 50% more of the atmosphere than when the sun is directly overhead. So at an angle, right, there is say the path length of the sun will be longer, and you can imagine because the longer path length, the spectrum of solar radiation reaching the surface will be different because the absorption of the atmosphere itself and scattering process, right? So you look at, let's say, 1.5, the angular relation, the actual distance is 1 over cosine theta. So cosine 48.2 gives 1.5. So this offers AM 1.5 offers when the solar is in this angle. The angle away from the perpendicular is 48.2 degrees. Okay, so that's the. But there are also different AF depends on whether the solar radiation we measure is directly coming from the sun, or there are also scattered diffuse light. So there are AM 1.5, there are different AM 1.5. I mentioned before, AM 0 is the spectrum of the radiation outside the atmosphere. And AM 1 is directly 0 degree. And 1.5 has 1.5 global G and 1.5 direct parts circum solar. So the direct one is really considered a small cone of solar radiation. And this cone is confined to 2.5 degree, let's say here, let's say 2.5, half lambda 2.5 degree surround the sun. And so this is the AM 1.5 direct. And then AM 1.5G is the radiation from the sun, the entire sky, the reflecting off the ground. And so in this case, the solar zenith at 1.5 is 48.2. But also the panel itself, okay, is tilted at an angle 37. So it's not a perpendicular incidence from the sun to the solar panel. Right here is 37. So the angle really the incidence angle of incidence is 11.2 degrees. So people typically use 1.5G for solar cells. Okay, so that's this is just a graphic illustration. 1.5 is at the 40, not 48.1, 48.2, right? And so the global equals the scatter light, and also the panel is 11.1 degree away from the normal incidence. Okay, so if you look at the spectrum, right, this is how the different gas in the atmosphere absorbs. And water is actually really the in terms of absorption is the worst. Okay, so this is the water absorption spectrum, different wavelengths. Carbon dioxide here is 10 micron, right? That's about the 10 micron range. Carbon dioxide in this band is what people worry most, right? Because you increase carbon dioxide, the 10 micron radiation from the Earth cannot escape. And in fact, if you combine all this, let's say the Earth warms a little bit more, right? And then there are more water evaporate from the ocean, and more water will trap more radiation. So there is that's why it's a very complex problem. And methane, nitric oxide, this scattering is the most severe in the blue region, and that's why the sky is blue. It's the scattering proportion of omega fourth power, frequency fourth power. So the short wavelengths scatter more, and sky is blue. You don't look at only scatter light. You don't directly look into the sun. So that's the solar spectrum. In terms of the absorption characteristics, and here is the spectral. So outside the Earth, you can say the blue curve here, right? And let's say when the radiation goes through the atmosphere, the absorption bands, different absorption bands here start to kick in, and the radiation is diminished when you reach the Earth's surface. And if you integrate all the solar radiation here, and you get the total radiation energy in the solar spectrum at the AM0 that's outside the atmosphere is 1366 watt meter square. So you go through, say, probably, I think, Professor Ali Sachs, he has a startup company for the 1366. Next time you can tell us if you saw him, even though that's the solar concept. Okay? And this is say, 577 Kelvin. So that's about the size of solar. Now let's talk about the surface itself. And I'm giving you the next few slides of definitions. And the key point I want to, you don't, you're not, say you need to know all the details. But the key point is that the surface properties, radiation surface property is spectral dependent, depends on wavelengths. It's also directional dependent. So those particularly later on we'll talk a lot on selective surface. That's the spectral dependence. And in fact, they're also directional dependent. You can control spectral and directional property of the surfaces. So the appreciation I want you to have is those, you can start with the basic property, like when I look at the emissivity of a surface, I can look at the different direction and different wavelengths, how it's emitting, the emission characteristics. So this is the light coming, the intensity emitted in certain direction, and I normalize to Blackbody intensity. That's the usually we consider that as the maximal, right? So this normalization is the directional, which I put a prime, so rotation-wise, and the spectral, which I put a lambda, so directional spectral emissivity. And it's a function of the temperature of the surface, the material. Temperature depends on temperature, depends on material, and also depends on surface finish, right? That's how we control the properties. You can have a piece of aluminum, which is very shiny, no emissivity, but you rough it, then your emissivity will change into much higher values. So that's a spectral, directional spectral, and then you also now you integrate all the energy. So this is the intensity. Here I'm talking about the energy now because it's emitted to all directions. If I integrate together all the energy going into the surface, but still at a certain wavelength interval, only at a certain wavelength, then I get a hemispherical. So that's over all directions, and spectral. And you can calculate. You can calculate from here to here. If you know this, you know everything. Okay. We just want to go through the concept, and then you can also say in each direction you integrate the whole spectrum. So we call that total. Total means all the wavelengths. Hemispherical means all the angle. So you have directional total, and then normally when you take an undergraduate course, you define emissivity. We typically talk about hemispherical total. That's the typical library. You look at table at a heat transfer rate. So that's the all direction, all wavelengths. Okay. So those are the definitions. And a surface, when we say how good it's in terms of the emission characteristics, if it goes or emitting in all directions isotropically, okay, intensity is the same in all directions. Blackbody is the one example. It's a diffuse emitter, so it goes isotropically in all directions. And if the emission is independent independent of wavelengths. So the directional emissivity is same as if you integrate all wavelengths in the same direction. So that's the gray is independent. Gray means independent of wavelengths. Diffuse means isotropic. So diffuse gray means so if it's diffuse gray, then in all direction, all wavelengths is the same, and then all those emissivity are the same. But fundamentally, you can start from here and write relation between all those properties. You calculate all other properties, you know this one. But this one doesn't always equal to the others. Okay? So that's the emissivity. And the reverse of emission is absorption, right? So if light comes in, and thermal radiation or light, and then the power really, I think I probably should have written here the small form, how much radiation come in, and the power absorbed in this, the fraction of the power that's being absorbed in this small form. That's the absorptivity. And again, here we have coming from a certain direction, so that's prime, and at a specific wavelength, that's lambda. Okay? So we define directional spectral, and then you do the same thing. You integrate all angle of incidence, they absorb as spherical spectral, and then all in the same direction integrate all wavelengths, or you integrate both wavelengths and direction. Same analogous to emission, except now the reference is what comes in. But let me just make one comment here. Although what comes in, the overall spectrum of, so for example, solar coming to the surface depends on temperature of the sun, right? But the spectral here doesn't depend on temperature. I can have the surface, this is thermal radiation coming to the surface, or this laser beam come to the surface. That's my intensity, right? And this temperature is really the temperature of the material. It's not the temperature of the source. So this is the absorptivity, and then selective is very important. Second law. Second law relation for emissivity and absorptivity. That's Kirchhoff's law. Okay? The Kirchhoff's law say this is the same temperature of the object. The directional spectral absorptivity, emissivity equals directional spectral absorptivity. Okay. Blackbody radiation is not a second law. The Kirchhoff's law is the equivalent of second law. The Planck's law, when I say blackbody radiation, I mean Planck's law, you can break it. Kirchhoff's law, you cannot break it. Okay? This is the second law. Fundamental, but remember, I'm putting down again, it's directional spectral. I don't mean the other property are the same. Now, if you have a diffuse surface, diffuse emitter, diffuse absorber, then this is fine. Then all the other property, higher level properties are also equal. But in general, they are not equal for higher order. It's only at this fundamental level, directional spectral. Like I said, the message is depend on wavelengths and the angle. And if you think about the reflectivity, transmissivity, so you have a piece of glass, right? So light comes in, you have reflection, and then light can go through. Of course, there are also absorption here inside. And the light comes in, the reflectivity is even more complicated because you can go other directions. You can go, one light comes to a surface, and this is a relatively smooth, but you can go diffusely to all other directions. So we then will have to say, incoming is one direction, outgoing is the other. So the fundamental definition is actually is bidirectional. What comes in, what goes out, the intensity. So you have two angles. One is the angle of incidence, the other is the angle of reflection. That's a bidirectional reflectivity. Let's say now if you integrate all reflected intensity, you got say the directional. When I say directional spectral, so that's coming in and integrate all angles. So if here when I do bidirectional notation wise, I have 2 prime. Okay, and when I integrate all angle of reflection, I get directional spectral. So this direction only means incoming because I integrate the reflection over all angle already. And then I have time circle. So this is now from here I can do the rest similar as I did for emissivity and absorptivity. So in fact there are 8. You can start with more fundamental and define all those other properties. And you can do the same for transmissivity. Okay, bidirectional transmissivity, and then integrate all transmitted light, and that's only one direction that releases things. So all these are the level of properties. Now, the energy conservation will tell us, if I think about the light comes in, right, and it's either reflected, that's the reflection of all angle, incident at one angle, and absorbed inside the material, or transmitted to the other side. So that's energy conservation. That's the first law. So in those relations, I've told you the first law and second law. You can't violate it in any of this, in any cases, right? So diffuse reflector, so similar to the what we talked about emitter, is when one light comes in, the reflected light go all directions. A really bad, say, surface, in the sense of light goes all directions. But in fact, a lot of time you do want this, particularly in some illumination case, right? You actually want the diffuse light to make the room feel comfortable. And so gray emitter is independent of wavelengths, and diffuse gray reflector is both isotropic and frequency independent. So if you, some of you to the undergraduate heat transfer learn diffuse gray surface means diffusive gray emitter and diffuse gray reflector. So it means both. We have come back to study diffuse gray emitter. Here is diffuse gray reflector. Okay, lot of definitions. So we're not going to use much. I just want to make you aware that the surface properties are frequency dependent, wavelength dependent, and directional dependent. And now there's another key concept. When I want to calculate how much radiation goes if I have an emitter, radiator. How much of my radiation get to you, right? So that's the concept of view factor. If I have one surface here, another surface here, okay, view factor is defined the power leaving this surface, okay, that's the total power leaving this surface, and intercepted by this surface. I didn't say absorbed by the other surface. It's just reaching the other surface. After reach, you could reflect it, transmit it. That's the that's not included in the power, say the view factor. Just say diffraction reached it. Okay, so that gives you a way of, if you think about the previous reflectivity, transmissivity, that's near the surface. This is just say how much goes to that surface. And if I use this definition, the power leaving the surface here is the EI, so that's the I should have multiplied pi. I think So pi, because the intensity times pi is the diffuse surface giving me the total radiation given the surface. And then this is the radiation, if I go back to the definition of the intensity, so this is the power in the cone times the solid angle that this area, dAj, suspended with respect to this point here. So that's dAj cosine theta, that's the lower area, and divided by r squared, that's the distance between the two surfaces. And this is what's the power in this cone and reaching that area. So with this definition, I have I still think that is a pi, but I'll check that. So I have a pi r squared cosine theta I cosine theta j dAj. So that's a different small area. The two surfaces are small. Does anybody remember this pi? Okay. If I integrate both surfaces, I get a total if the surface is uniformly median, right? And so that's the view factor. Those kind of view factor, again, you can look for tables. One way is go to do this calculation, but for a lot of standard geometry, people have done the calculation, so it's calculated. And the assumption I made is that over this surface, the radiation is diffuse. So I said I have a pi times I. And then radiation, even the surface, the whole surface is uniform. So that's the assumption I'm making. And I said you can look at the tables, but there are also relationships. If you look at the definition, it's very symmetric, right? So from this, you will see the reciprocity relation from view factor from A to J is times the area I, and it equals from J to I times area J. That's a reciprocity relation. And if you do the total, we have. And then the summation. Summation is basically the energy balance. The energy leaving surface I will reach J, combined surface I plus K, then it's the same as leaving I reach J and leaving I reach K. First one. Okay? So with those relations, the view factors, most of the time you can, for simple geometry, you can find it from table, or you calculate using this relation rather than doing those complicated integral algorithm. Let's go look at the Earth and Sun, right? So the Earth and Sun, because they are so far apart, essentially I can treat them a very small surface relative to each other. So it's a D area. And rather than look at the curvature, because when I look at curvature, each point will be different angle-wise, perpendicular to the surface. And in fact, you can just treat this as a disk, and this as a disk. It's equivalent. Okay? The disk area operates pi d squared over 4. And then I look at the view factor from the Sun to the Earth is the Earth's area divided by the distance. So very small. And from Earth to the Sun, so how much radiation even Earth reaches the Sun? That's the fraction, right? This is the fraction radiation even the Sun reaches the Earth. That's here. Here is the reverse, and because the Sun cross-section area is larger, the view factor from Earth to Sun is larger. Fraction-wise, more radiation even here than here. Right? So that's the relate. First, you go to check the reciprocity is satisfied. Okay. Now I want to calculate the solar constant. Okay. Like I said, 1366. But I want to check radiation reaching the Earth from the Sun. So this is the black body from the sun. Definitely if I approximate as a black body. Times the surface area, the disk area, AS, times the view factor from the sun to the earth. Right? So that's the total radiation from the sun reaching the earth, intercepted by earth. And I can use the reciprocity to get a per unit area, right? Because the AS times the SE, AS, SE, FSE equals the AE Earth, FES. So when I do per unit area, I normalize, I use the reciprocity, I will actually write this as the sun emissive power times the Earth to sun, here it's sun to Earth, but the area gives me the Earth to sun view factor. Oops, I forgot this number. So this is the Stephen force level -8. I was just reading an error, sorry for that. -8, temperature force power, that's the sign 5.67 10 to the -8, 577, that's the sign temperature, times this factor here, 679. I did a calculation, what I got is 1365. Pretty close. And Schroeder's constant that you integrate is not exactly flat body. So this is why some people say the equivalent is 5777. Okay? Schroeder constant, right, is 1366. Okay? Now, let's look at so that's the energy coming from the sun to the earth. What's the maximum efficiency I potentially can get? What's my best luck? If I can convert the solar energy into mechanical or electrical energy, the maximum using thermal process, thermal engine, right? Thermal engine, of course, is limited by the Planck's law. The Carnot efficiency. So you can always say it's the Earth temperature and the sun temperature. You drive a power efficiency between the two, and you will get 1 minus 300 divided by 5777, which is about 90%. That's an absolute possible. Suppose you can somehow tap into sun directly, right? Of course, we can't put anything in contact with sun. And so let's dream up this process. I have a black body of the sun very close to my absorber, right? I see this is the very close because in reality it can't be close, but I can focus the solar radiation. And it turns out that if you do the focusing, and the maximum you can get is something like a solar temperature. So the black body at the sun, and the absorber, if I absorb all the solar radiation, so here the absorber is also black body. And then say I add this temperature T, and then I put the engine in between this absorber and the ambient, and the output, and I can imagine this engine is perfect, the Carnot engine. So what would be the efficiency of such a say system? And first I want to say how much heat can go from the sun to this absorber, right? Here I'm doing two black body, so black body radiation is from sun sigma T force power. You can see now I don't have this very small view factor, right? I'm just doing two parallel plates, okay? So sigma T force area is no area difference anymore. Sigma T force power minus this radiation now, the absorber will radiate back, so minus T force power. So that's the heat transfer from the sun to this absorber. Okay, maximum you can get. And so that means the thermal efficiency, right? What comes in the solar is sigma T force power, and the amount of heat transfer that actually should happen is T force minus Ts force minus T force. And the thermal efficiency is the 1 mass temperature force power ratio. So the higher the temperature is the absorber, the lower is the thermal efficiency. And now I put the color in between. So the color efficiency is here. Okay. And in fact, as I move on, you should ask questions because the question is, what if I use selective surface? Okay. Why you put a flat body here? And this will be related to what kind of concentration, how you concentrate. Because here I'm really putting the maximum temperature, really like this is the sun, this is black body, they are facing each other, right? And that will require you put your maximum concentration. And in the case of maximum concentration, the emission of this surface becomes not important. It's really the absorption that's most important. Absorption, the higher the better, the best is 1. So you get a black body. That's why. So now I have a thermal efficiency, I have color efficiency, and the product of the two gives me the maximum the combined efficiency. So this is the thermal efficiency. This is the color efficiency. Of course, the color efficiency, you want to operate your engine as high temperature as possible. The thermal efficiency, as you operate the higher temperature, radiation loss increase. So you have a maximum here. So this is the maximum efficiency you can get, about 85% efficiency out of the sun. And this happens around 2450 Kelvin when you have amplified 300 Kelvin. What's interesting is actually there's a pretty wide range. The efficiency, this is actually really good, right? Pretty flat, relatively flat. Okay, and so if you think about here is only about 1,000 degrees. Here is 4,000 degrees, and this is 70%, right? Pretty good if you can get it. And we know the coal plant is only 40%. The combined, that's the coal burning plant. Coal plant is about 40%, and if you combine gas turbine and combined cycle. Combine gas turbine with the steam turbine. So you burn fuels, you generate hot gas and gas profile turbine. Say gas turbine and exhaust generate steam drive with steam turbine. That combined about 60%. Okay, that's best you can do with the fuels. And internal combustion engine, the car is about 25 to 30%. So that's the so this is a pretty optimistic value here. So if you put your solar, if you put a thermal engine between using the heat from the sun, right? But of course there are many limitations. Okay. Now the next question I want to ask is, if I put a material here under the sun, how hot it can get? what's the maximum concentration here? Okay. And I could imagine a case where it could potentially get to very high temperature. And this radiation comes in, it will be absorbed. Now I don't think about the direction. Let me just say all direction is same. And again, because of that, maybe you have ways to do better. I don't know yet. So radiation comes in. The absorptivity of the surface is a function of lambda wavelength. And then also the emission, it will re-radiate, right? So absorption, if I do directional, I know the Churchill's law tells me absorption equals emission per wavelength like this. At least if I say directional wise, it's the same. So it's all diffuse, you can imagine that. Okay, so when I do this, I will have the absorbed energy. This is the you can say this is the spectrum from the sun, and times absorptivity. Clearly, I have integrated over angle, right? And integrated over V lambda. So that's all the energy comes in. And then this is the energy that is re-radiated. One is the surface radiation, emissivity times Blackbody emission, this Blackbody emission temperature T. But also the ambient is so you have the heat exchange between here and the ambient. So this is the radiation to the ambient. T should not be T0, T and here I have concentration. As I said, this may not be, I think this probably is not a maximum. Well, as I talk, I'm just making comments. Because the radiation from the sun is in a very small angle, right? It's almost lower incidence, you say lower incidence. And when I write this emission, I'm writing the emissivity isotopic. I could potentially design surface emission only also in the same angle where the sun comes. Then I have to do angular integration that probably could go even higher temperature than this if I just make that guess. Okay? So once in terms of the the spectral characteristics, right? So if you look at, this is the radiation from the sun, and this might be the radiation emission from a heated surface, and at each wavelength, right? So you can design your selective surface, ideally. You can design it if you could, okay? Seriously, now seriously not. But it's hard to do. But let's just say, imagine I have that magic surface that I have a sharp cutoff. So below certain wavelengths, all the radiation is absorbed. So that could be the solar radiation, right? And then beyond that, all radiation is rejected. So that's the spectral idea, 1, 0 spectral properties, selective surface. And so if this selective surface is a 1, 0, and I can look at, if I design the selective wavelengths here, if you look at it, right, this Blackbody from emission reduces rapidly. So if I make my wavelengths here, this radiation Churchill's law, then now I have to remind you of Churchill's law. When I say the spectrum, this absorption is 1, I also mean the emission is also 1, right? I can't violate that. So this radiation will be going out. This blue in this region will be emitted. if I absorb everything from the sun. That's the second law tells me. So if I have, I change this wavelength, you can say now I make the wavelength shorter. There's less emission from the blue curve, because here is almost zero, but there's still a fraction of the solar radiation that comes in absorbed, right? So I want to do my energy balance and say, what's the maximum temperature I can get just with a flat surface, one sun, okay? So C equal to 1, and I do, rather than do a Blackbody spectrum here, I was trying to do this by hand, and then later on I found that I still couldn't solve the equation, so I get the team again into my office. He has a code that you calculate a few curves, you'll see later on. So here is the radiation from the sun, and I say absorption is 1 between 0 lambda. So this is 1 times whatever comes from the sun. So view factor from sun to Earth surface, the surface area of the sun, Blackbody emission of the sun, d lambda. That's what comes to the Earth surface. And this is the emission, radiation out from the surface. So I'm assuming this surface is facing the sun directly, right? There's no angle tilt. And emission out and emission to the ambient. Within the ambient. Okay. And of course, let's say I used this trick before. This area times view factor is the same area on Earth times the view factor from Earth to the sun, so that I can cancel the area. So it's independent of area here, right? I can cancel the area, and that's why I was doing the universal Blackbody curve. So if I do my universal Blackbody curve, this is the radiation between the sun temperature, anion wavelengths normalized to sun temperature. Horsepower, this is the function I want to find the temperature. I thought I could do this by hand. Again, this function is not that linear. I can't, you have to do it iteratively to solve for the temperature. Okay? So, but this is definitely solvable. You can go to solve the equation. You can even take the real spectrum to solve it, rather than doing Blackbody spectrum as I'm doing here. I've written down, in fact, that's what the Chen has done. This is the curve, AM0 condition, and if you choose your wavelengths, it's interesting that the shorter the wavelengths you choose, the higher the temperature you get. That's because the loss is smaller, right? You look at it, you go to shift to small wavelengths, you absorb the radiation, but you lose very small. Because this curve, once you go to very short, this curve is always below the effect of the Blackbody curve of the re-emission. And so your, but see, isn't this amazing if you have that surface here?
In my old house, I boil my water with sample.
Oh, water heater, yes.
Oh. Now it's black, it's water you see.
Yeah.
No concentration and no, let's say no optical treatment, no filters.
Right.
It's definitely not 600 Kelvin.
No.
It's 81 Celsius.
Yes, what is that? Is a flat panel?
Yeah.
Flat panel, yeah. Flat panel, you got a lot of losses. First, the surface is not bad. The battery industry has done a pretty good job. And you can buy, this is part of the thing that I'm going to talk later. You can buy commercial, this hot water surfaces have a 95% absorption, 5% emission. A lot of sharp product, we'll have the example later on. And not a flat panel, it's not a vacuum. You take a vacuum tube that China used, you put it in the sun, you go to 200 degrees Celsius. Right? That's when you don't have water inside, it's just dry. It will go to 200. Okay. Yeah. So this is the I guess the point is, if you can design, right? Here is if you recall, for a thermal engine, 85% efficiency range or 70-85, right? You need 1,000 to 4,000 temperature range, theoretically. And here, it doesn't seem to be that hard, right? If you got that surface, of course, that's a really ideal surface. Right? You can get into 1,000 degrees, even with one sun, flat. Sorry. And here is another example in 1.5. That's the top of the Earth. And again, ideal situation. Okay. Now, but those ideal situations you can do almost this doesn't give you any power, right? What we did is just to say is comes in equals to the loss, no power, right? So now let's look at the more realistic case where this is still the surface idea, but I don't optimize the temperature, trying to reach maximum temperature. I try to say, given a temperature of operation, what's the I choose the wavelength. So the way I choose wavelength, if I say this is the curve here, what radiation comes in from the sun, and at this wavelength, the black body at this temperature, the black body intersect the solar radiation at this temperature, at this wavelength. So I cut out this point, and then below this wavelength, I have 1, above I have 0. So the difference from the previous discussion is previously, I say at each wavelength, what's the maximum temperature? And here is I give a temperature, I choose my wavelength, okay? And then I say if I operate the heat engine at this temperature, what's the efficiency I can get? Okay? And so this is the same picture here. Now, other than fitting this just as the black body, two black body working together, I say I'm looking at the one sun condition. Okay, again, like what I said. Now, in this case, the thermal efficiency is what comes in the total, and then this part is lost. The blue curve part is lost. Right? So if I calculate the thermal efficiency, and this is a King mechanics calculation, and as you here is the thermal efficiency. So the loss is this is the larger, the blue, the purple area is the dark area. This is a 0.9 high thermal efficiency. So naturally, if you want to have a good thermal efficiency, you don't want to radiate it out heat. So you want to operate again at a low temperature. You go to low temperature, like Kelvin. So that's but of course you get 0 calorie efficiency. So you still got the optimum, right? So you multiply this to the calorie efficiency, and this is the transition wavelength Q2. And so this is in this case what you have is 0.5. So still pretty ideal, right? Pretty good, very good. You can get even half of that. Okay? Because 50%. Let's assume you have a thermal engine, right? Power engine operate between, in this case, let's say here is 50%. So the power engine operate between 800 Kelvin to room temperature. Okay, and of course, if you have a real efficiency, less power, So most likely you are shifted to lower temperature. This is actually a real selective surface. This selective surface is from Sun Select. This is the emissivity, the solar in the solar region, and in the IR region. Problem is nobody could make this really sharp. Okay, it's a transition. There are always a transition. The sharper, the better. And so if you use this surface to do the calculation, real surface to do calculation, and again, assuming a color efficiency, so here is the system efficiency now becomes about 30%. And you operate you don't want to operate at high temperature. You see here. The optimal is actually pretty low temperature, except that you need a device converter that work at the color efficiency here, right? If you recall the solar cell, say Shockley-Queisser paper, right? Shockley-Queisser limit for single junction solar cell, silicon solar cell, the maximum efficiency is about 28%. Look at this. Yeah, this is very good. Okay. And of course, solar cell is also thermal energy. It's limited by this efficiency, power efficiency. Whatever limit we're discussing here, except that the emission. No, not this one. I'm sorry. The emission, solar cell does not have a re-emission problem. Right? So it's a matter of the what's about the band gap times the color efficiency limit of solar cell is the solar cell is itself operated at low temperature. So the color efficiency limit is really from the sun temperature to the earth. That's the operator. And if you do, it turns out that if you do infinite multi-junction solar cell, the maximum efficiency is still at 85%. Same upper limit. Okay. So those were the previous discussion were done for the concentration equals 1, right? One sun condition, and you can add other concentrations. And these various kind of absorbers, and this is we have Blackbody absorber. This different concentration. We can say this is the concentration, and that's the temperature of operation. Here is the efficiency, and now you use a more realistic absorber. The Blackbody is just the overall spectrum. Let's say here is a selective absorber. That's so you get a higher efficiency. And if you compare these two, you also operate at a higher temperature. So here you got to operate at a higher temperature. If your selectivity is good, you can push to a higher temperature. If your selectivity is not good, spectrum is not good, and Blackbody, you don't want to operate at high temperature. You want to operate at low temperature because you're losing too much heat. So the solar thermal engine is always the fight between the losing heat by radiation and the color. The thermal engine want to operate at higher temperature. Your surface don't want to operate at high temperature. So there. And now if you go back to even the ideal absorber means 1 and 0 selectivity spectrum, right? You push to a higher and higher temperature depends on your concentration ratio. Okay. So those were the general discussion. The message is, if you can do good spectral control, you can get a high temperature. Right? So that's to say, spectral control is really a critical problem. And we're in our DOE Department of Energy Research Center, we have two parts. One is look at the, for example, thermoelectric. The other is really look at the spectral control. And in fact, later on, we'll talk more to thermal photovoltaic. And you realize that you're transforming one difficulty into another difficulty. In solar cell, the difficulty is a single junction cell is limited to Schottky fiber. That's the limit. So you try to do multi-junction cell, which people have reached about 41%, 3 junction. But say infinite junction, you can get to 85%, right? So, but the growing material to more than 3 junctions is very difficult. And now we transform one problem into this difficulty into another difficulty. If I can have a selective surface, right, really ideal, how to work at a high temperature, then I can potentially get high efficiency, even with single junctions. So, but of course, this has now a lot of engineering aspects, because let's suppose when I have this ideal surface, right, selective surface, absorptivity, emissivity, on the other side, you can hardly design a surface really zero emission, so this side will lose radiation. And also, you have to hold it somehow, 1,000 degree, 2,000 degree. You have to hold it. And of course, you can use, let's say, a suspension. You can use, think about, this is actually if you do this solar, this is the one advantage I consider solar. If you do with a combustion chamber, it has to gas contact or a very sturdy structure, right? And this way, in the case of the sun, what comes in, let's suppose this is a vacuum chamber. What comes in, those photons can go through the glass, right? Then you have much less in terms of the complexity dealing with the hot gas, the phasor contact. You can use a really short, say, very small string to suspend your surface. So that's one advantage that which is probably better if you do the solar compared to thermal source. So here is the suspension, and of course, if you have suspension, then you have heat loss. So you have to count for those other heat loss, suspension, and other emission losses, and so it's they become a careful engineering problem. That's why at the end now, even you work on the solar thermal photovoltaic, you have to go back to basics of how conduction, heat leakage through any heat leakage. Those are part of the degradation factor for your system applications. Any questions?